Another challenge is to capture data from dynamic systems. The Global Precipitation Measurement Mission, or GPM, is the next generation of satellite-based precipitation estimates that will offer global coverage that refreshes every 3 hours. It will be the successor to the Tropical Rainfall Measuring Mission, or TRMM. The GPM mission involves the use of radar on a core satellite tied into a constellation of other satellites. This will improve weather, climate, and hydrologic predictions.
The radar on that core satellite is similar to the TRMM radar, but has lots of improvement because we are going to use two frequencies, dual frequency radar on the GPM core satellite. That's a big improvement. By using two frequencies, we should be able to have a more accurate estimate of rainfall rate, and also we'll probably be able to distinguish the phase of precipitating particles, whether they are rain or snow.
One of the main objectives is project future climate and also predict weather. For that, we need both observations and the models. The models itself won't do the job because models are set of equations. We need to calibrate those models with the observation to start with. Once we do that, we can rely pretty much about what it says about the future. Hence, there is a way we need to combine both observations with the models so that we can come up with a pretty good accurate forecast models or forecasting climate for a long term.
CloudSat is an experimental satellite that uses radar to observe clouds and precipitation from space.
CloudSat represents a brand new way of looking at the atmosphere. This is the very first space-borne cloud radar. It is giving us views of the atmosphere unlike any that we've ever seen before. We're actually able to see inside clouds, not just the tops, which are basically what we've seen from space using passive sensors before. And we're actually able to see inside and all the way through clouds, giving us a view like we've never seen before.
We have a pretty poor ability to measure the water in the sky over the entire globe. We do it presently, before CloudSat, we deal presently with basically with cameras, with imaging instruments that map the cloud distributions, but it doesn't tell us how much water is in the sky, it doesn't tell us what fraction of these clouds produce the rains that nurture life, basically. CloudSat flies a really unique radar and operates at a very much higher frequency or very much smaller wavelength than typical weather radars. And what that allows us to do is see the water both in the form of clouds also in terms of the precipitation. So we can actually see rain being created inside the clouds.
Looking ahead, satellites will become increasingly effective in Earth observation, but there are limitations to overcome.
We started off a long time ago with a real problem, and that was the fact is that we couldn't build instruments that could produce observations with a high enough resolution at the Earth's surface. With working with these low frequencies in the microwave region that we need to work with, we're limited in terms of how large an antenna we need in space in order to achieve a high enough resolution at the Earth's surface.
But there's another challenge as well, a technical challenge associated with computational abilities. Can we undertake distributed computing in a way where we can solve extraordinarily difficult problems with meaningful numbers of resources? So observations in remote sensing as well as modeling and computer capabilities are two of our strongest technological challenges.
I expect a lot more capabilities and a lot more advances associated with the enterprise as a whole. The prediction side, we're getting much more sophisticated in understanding some of the basic physical, biological, and chemical processes and how to model them. Our computational facilities will continue to grow over the next decade that allow us to increase the resolution and timeliness of forecasts and to be able to connect those forecasts and predictions with decision-making models, whether it's an economics model or an ecosystem model or a basic operational model of a reservoir.
In addition to these technological hurdles, other barriers have become apparent, particularly in the sharing and use of information.
There's a tremendous gap still between the information that has been produced and where it is used. So first we have to make sure that we allow information, or meaning sensory data, to flow. And so it is at that level that we are working on this infrastructure, to develop the appropriate standards so that if there's a new satellite, a new surface network that is available, that provides data, then that is now automatically, at the very moment when it comes up, automatically can be entered into the distribution stream that knows how to digest it and turn it into that high-grade, very context sensitive and context-tuned form